Okay, so here's the first example. Sum n equals 0 to infinity, x minus 1 to the n, 3 over 3 to the n times n plus 1 cubed. And we're asked to use the ratio test to determine the radius of convergence for this series. So firstly, I want to recall the ratio test. Okay, and remember, the ratio test was written in terms of a series, not a power series. So when you're applying it to a power series, you have to think of x as fixed and as the x minus a to the n as being part of the a to the n. So the ratio test, if sum an is a series, consider L defined to be limit n goes to infinity, absolute value of an plus 1 over an, if, first option, L is less than 1, then the series sum an converges absolutely. Second option, if L is greater than 1, then sum an diverges. Option 3, if L equals 1, then the ratio test is inconclusive. Okay, so let's consider applying this to this example. Now remember, we have to think of x as being fixed. So for fixed x, okay, because you want to think of the x minus a to the n as being part of the an. So here our an is the entire piece, the x minus 1 to the n over 3 to the n plus 1 cubed. So then, following this formula, what's an plus 1? Well, everywhere we have an n, we just replace it with n plus 1. So we get x minus 1 to the n plus 1 over 3 to the n plus 1, open brackets, and n plus 1 is n plus 2. Okay, so L is going to be the limit, as n goes to infinity, of an plus 1 over an. Now remember, if you're dividing by a fraction, it's the same as flipping it and multiplying by it. So we're going to have x minus 1 to the n plus 1 over 3 to the n plus 1 times n plus 2 cubed times, and now flip an. So 3 to the n plus 1 cubed over x minus 1 to the n. So we get the following cancellations, the x to the n plus 1 and the x minus 1 to the n plus 1 and the x minus 1 to the n, and the 3 to the n with the 3 to the n plus 1. And we're left with x minus 1 over 3 times n plus 1 over n plus 2, and I bring them both inside the cube. And this just leaves us with x minus 1 over 3, as the cubed piece just limits to 1. So if we want L to be less than 1, then this is exactly the same as absolute value of x minus 1 being less than 3. So that tells you the radius of convergence around 1 is 3. Okay, so that's the first part of the question answered. Okay, so moving on to part B and part C. Part B, what are the values of x at the end points of the interval of convergence? So remember, this was the condition, absolute value of x minus 1 less than 3. If we were to draw that, this is centered at 1, and it means we can go 3 either side. So we can go to the right up to 4, and we can go to the left down to minus 2. Okay, and that's it. That's the two endpoints. So x equals minus 2 and x equals 4. And remember, you have to test these 2 points individually, because the ratio test will give you that L equals 1 if you were to plug these 2 values in. And we know that that's inconclusive, so we have to test it individually. Part C, write down the series you would have to check for these tests. So fill in minus 2, fill in 4, and look at the series. So x is minus 2. Let's fill that in. Sum n equals 0 to infinity, minus 3, minus 2 minus 1 is minus 3. 3 to the n plus 1 cubed equals we can break up the minus 3 to the n as minus 1 to the n times 3 to the n. And of course then the 3 to the n's cancel. And we're just left with sum n equals 0 to infinity minus 1 to the n times 1 over n plus 1 cubed. Okay, let's look at the x to the 4, or x equals 4 case. So then we're going to get sum, and instead of minus 3 to the n, we'll just get 3 to the n over 3 to the n plus 1 cubed. And similarly, we just cancel the 3 to the n's, and we're going to get sum n goes from 0 to infinity of 1 over n plus 1 cubed. Okay, now we haven't yet developed the tools to decide whether these two series converge or diverge, but we'll develop the tools in a later lecture.